Because when there is a fraud, let's say that someone wants to steal the money from your credit card, you want to detect it as quickly as possible. If you can detect it in real time, great, you can block the transaction. If you detect it 1 hour later, well, it's probably going to be already too late. So I will start with the first use case, a company called OpenX, where I used to work as a senior data developer. And OpenX, one of the products that OpenX used to do is open source ad server. And the challenge that we were facing in there constantly was just a huge amount of data that we needed to process. And I worked with many customers using this open source ad server. And the kind of standard problem that we've seen all the time was that the customer wanted to ask for some sophisticated analytics that very often weren't additive. If you have additive statistics such as, I don't know, simply counting number of clicks, it's very simple to do it because you just count the number of clicks in 1 p.m. and 2 p.m. and sum it up. But if you want to calculate the statistics such as, I don't know, unique number of viewers, you cannot, it's not additive. So you cannot just calculate the number of unique viewers in 1 p.m. and then at 2 p.m. and add it up, because some of those users will repeat. This is just a simple example, but you can also apply it to something like percentile or standard deviations and so on. So one of the easiest things that you can do in such a situation is that you can get the sample of the data, calculate your statistic that you are interested in on the sample of the data, and apply the statistic to the population. Use it to estimate the same statistic on the population of the data. The problem is that it's easy to create the sample of the data if you have all of this data stored somewhere in the database, because you know exactly how many data points you have. If you have 1 million data points and you want to create the sample of 1,000 points, you simply choose every 1,000 element from your database. But if your input data is a data streaming, you don't know how many records you are going to have. Maybe all you will have is 1,000 elements. So you do not want to choose every 1,000th one. Maybe you will end up with 1 million, maybe you will end up with 1 billion. Well, the solution to this problem is the algorithm which is called Reservoir Sampling, which allows you to find the sample of the desired length from the stream of the unknown length of the data. And we have a look at this algorithm. It's actually very, very simple. So don't be scared of the math. So in the first step of the algorithm, we simply choose the first. So let's say that we want to create the sample of size n, where n is 1,000. So in the first step, we simply put the first 1,000 of elements into our sample. In the second step, we create some probability that will decide whether the next element should actually go into our sample or not, and if we select element that it should go into our sample, then with some probability, we replace one of the elements in our sample. So as you can see, there are a few variants of this algorithm. If you will look it up, a very good paper is written by Maldonado, published back in 2011 on the subject. But the idea in here is that if you create a sample in this way, your statistic that you are going to calculate it on the sample will have a very good statistical properties, meaning you will be able to, your statistic calculated on the sample, you should be able to apply it very nicely to your population. Now, the second example of the data streaming algorithm is something which is called sketching. Sure, go on. I would probably prefer questions on the end because it's like quite a lot to go through. So, okay. So the second idea, the second type of algorithm that we can apply to streaming data is called sketching. The idea in here is that we want to convert some high-dimensional data, high-dimensional problem into some simpler representation, into the smaller dimensional space. And we can use that smaller, simpler representation to estimate some kind of statistic that we want to calculate. It sounds very complicated, but as you will see in practice, it's actually can be very, very easy. So a good example for it is, let's say that we want to count all the number of words ever written in any of the Shakespeare books. Okay? So the naive solution to it is pretty simple, as you can imagine. We can just create some database with all the words, and we can scan one word by word in every single book and just keep adding it to the database. And then we simply do select, count these things, and we have the number of words. Well, it's all great as long as you know your input data set is pretty small. But as soon as you are going into something like terabytes and terabytes of data, this algorithm is not going to perform very well because the database with those words that you have to create is going to be pretty huge as well. And it might not fit into memory, and you run into lots of problems. And so it will take time. Well, it turns out that you can actually do it in real time using some of the sketching algorithms. So, for example, to count all the number of words of the Shakespeare, you can use something like log-log algorithm. Again, there is a very good paper published by Durant and Flyolet back in 2003, where they show how to do it. So, using this algorithm, you can create the sketch of the data, which looks like this, which basically represents all the words. You can estimate the sketch to calculate the number of all the words in all the books of the Shakespeare. And it doesn't really look very convincing, but I will tell you exactly how this algorithm works, so it will be much easier to understand. So one use case for this algorithm, which is very useful, I think, is a company called Orange, where I worked on one project where we had to calculate the number of unique visitors. So we had around 100 million visits per day to the server. And the challenge was that you cannot really solve this problem very easily on the traditional relational SQL database. So we ended up using Hadoop MapReduce. And it worked actually pretty well, except it took probably a few hours to calculate and a few servers as well. And using something like log-log or HyperLog Log in this case, you can do the same in real time. So rather than using few servers and spending few hours, you can basically get your records straight away. So HyperLog Log is a highly effective algorithm to count number of distinct elements in your data set, in this case, number of unique users. A very good example of this implementation is you can find in Redis. Redis have one of the data types that you can use in Redis is HyperLog Log. So essentially, you can just put new records in there, and it will give you the estimate of number of unique users in real time. But let's have a look at how this algorithm actually works in practice. So first thing to notice is that it's not 100% correct algorithm. It will give you estimate, but this estimate is pretty good, like around 98.5%, which to be honest, in most cases is good enough. To understand how it works, imagine that we are flipping the coin. So you are flipping the coin, you have a head or tail. And now, how do you estimate how long someone was flipping the coin? Well, one way to estimate it is to ask this person to count the number of consecutive heads that they ever recorded. So you keep throwing the coin and you, for example, say that, okay, I managed to have 3 heads in a row. Someone else will say, I managed to have 10 heads in a row. As you can imagine, that second person was either very lucky to have 10 heads in a row, or most likely was throwing that coin for a much longer time. And now, using statistics, we can actually calculate exactly how many times, on average, someone needed to throw the coin to get 10 heads in a row. Okay? And this is exactly how the HyperLog Log works, except in here, instead of coins, we have the input data, which we hash, and the output of the hash is basically some kind of number. So when you run MD5, you get the number, and the number is represented as a binary, string of 0 and 1s. So we count the number of zeros in this output, and that's our heads, essentially. So now the idea is that the more records you put into the database, the higher are the chances that you will have, for example, like 10 zeros in a row, or maybe 20 zeros in a row. And this is it, pretty much. So we just hash the numbers, we put it into our data structure, but we actually don't put the numbers into the data structures, but we keep counting the zeros in there, and we just only keep the highest number of zeros we ever had. So that's all great, but sometimes you cannot really use these algorithms are very, very powerful, but sometimes what you want to use in practice is some good old, statistical methods written in something like R. So R, as probably everyone here knows, is the open source statistical programming language, so the cost of adoption is very low. It's very useful in prototyping, in statistical modeling. You can do visualizations in it as well. There's a very large global community of R users. It's estimated to be bigger than 2.5 million of R users around the globe. And the great thing about this is that many of those users are creating and publishing their open source libraries and packages. In the CRAN, which is like an open source database of libraries, there's around 5,000 libraries and packages which you can simply download and use to solve your problems. And chances are that the statistical problem that you are trying to solve, you probably find the solution to it in one of these packages. As you can see on this diagram on the bottom, it's actually the popularity of this language is increasing recently, which is quite interesting and exciting at the same time. I reckon it's probably coming from the fact that we have so many data scientists nowadays who are trying to understand their data, and many of those data scientists are using R. And indeed, you can see that many companies try to integrate their software so you can use it together with R. Like, for example, you can use R together with Oracle nowadays. Microsoft just a few days ago announced that they're going to acquire Revolution Analytics, which is one of the biggest, if not the biggest, R consulting companies. So it's definitely, I would say, worth looking into R if you are not sure. Now, the next use case I wanted to show you is from a company called Ad4Game, which is a gaming ad network. We show online advertising related to computer games in this ad network. We have roughly around 150 million ad views per day in here. And to analyze this data, we use, few software packages. So first we use Storm, but also we use Hadoop. So we have this so-called Lambda architecture. When you have two parallel processes, one in Hadoop, which is doing the batch processing, where we store all of the data and we analyze it in MapReduce. And the second, which is using Storm. And Storm analyzes all the data as it flows through the system and does some sophisticated statistical computations on it. So now, before we adopted Storm, one of the biggest challenges that we had was that the statistical computations that were arriving, it was a batch processing. So we would have new calculations ready every 1 hour, roughly. And now, one of the problems is that if you have some machine learning algorithm that is going to predict which of the ads are going to perform very well, when you do you try to select significant ads, you have to use some kind of threshold. to select them based on the p-values. And if you have many ads, like thousands of ads, you're always going to make some mistake. Just it's the law of big numbers, pretty much. So if you make a mistake and the next calculations will happen after the next hour, the problem is that you are going to be stuck with those bad ads for the next hour. You are going to display advertising that is not good for business. Those ads are not so good in practice as you were hoping for. So once we moved to Storm, what we managed to do is, well, we were able to do the same calculations in real time, essentially. You know, after every single click, after every single impression, ad view, we were able to recalculate the statistics. And this way, you still make some mistakes, but you are able to correct them, you know, as soon as there is a new click or the new view. So the solution I wanted to show you in here is how to do something like that using Storm and R. And I will also show you the algorithm which we use to select the ads, which is based on the beta distribution. But first, let's have a quick overview of the Storm. So Storm allows you to do real-time calculations on your stream of the data. Many people say it's a Hadoop of the real time. It's a fault-tolerant software, so you know it has this self-healing. If you run it on the cluster, one of the machines goes down. It's guaranteed that you are not going to lose any data. That data is going to be replicated to other machines. It's very easy to scale, so it's written in the scalable way. You can run it on hundreds of servers or more. It's very easy to develop new software in it. It has a local and a distributed mode, so you can write your program, test it on your local PC. Once you are happy with what you wrote, you know, it's working, you can deploy it to the cluster. And one feature that is very useful in our case in here is the Storm multi-language, which essentially allows you to use pretty much any programming language together with Storm, as long as this programming language can read from the standard in and write to the standard out and implements the Storm protocol. So a bit of more background to Apache Storm. It was open source in September 2011. After some time, the company called Twitter acquired the developers of Storm, and it was developed later inside Twitter. Nowadays, it's part of the Apache Foundation, so you will find it under the name Apache Storm. The implementation is pretty short, I would say. 15,000 lines of code for such a program, it's not much. It's probably mostly coming from the fact that it's written in Clojure, mostly. Clojure is this Lisp-like language which is working inside the JVM, Java Virtual Machine. So you can use it together with Java. And as we said before, you can do stream processing on it. You can do continuous stream processing as well. So you have your software running all the time, and whenever there is a new data coming on the input, you know, you do some recomputations. But very nice feature as well is distributed RPC, distributed remote procedure calls, which you can actually use to, so imagine that you can write your software in something like Python or R. You can deploy it to Storm, and you can essentially distribute your entire application on the cluster quite cheaply this way. Storm guarantees the message processing, meaning you can expect that if you use it, you should not lose any data. You can also use some kind of transactional processing in here, meaning that if you have a batch of the data, so you can do some batch processing in here, where batch is, let's say, 1,000 elements. So if you do not want to recount the same data a few times, you can use transactional topologies. And the last feature I wanted to mention is something called Storm Trident, which is like a pig or a hive for Storm. So it's a higher abstraction API which will allow you to be quite productive with developing your... All right, so we need to hurry up. So a few words about the Storm architecture. We have, well, if you're familiar with Hadoop, it should be quite easy to understand. So in Hadoop, we have a Hadoop job tracker, which is a master. In here, a master is called Nimbus. And all the work is done by the supervisors. And the state of your cluster is managed by the Zookeeper, which is a software for coordination and state management in the cluster. And the idea is that when you create your new topology that you want to use to analyze the stream of the data, you send it to the Nimbus, and Nimbus is going to distribute it across the server, across all the supervisors. And the supervisors are the ones which are actually doing, executing the work. From the software point of view, the way we create the data stream analytics in Storm works in such a way that we create two types of tasks. So we have spouts, so-called spouts and bolts. The idea here is the spout is the input of the data. So the spout will going to stream the data into your topology, and the bolt is where your logic is going to be, which will analyze that data streaming through your system. So as you can see, it's a graph of computations. So it's up to you essentially to decide how this data is going to be streamed through the system. So let's say that we have some input data coming from the logs. We want to have, in this bolt, some kind of computations that will look up the data perhaps